Hi, in this video, I will demonstrate how to identify the eigenvalues and eigenvectors of a matrix. The scalar denoted by the Greek letter lambda is called an eigenvalue of the matrix A. To help us solve eigenvalues, let's have the theorem about it. Let A be an n by n matrix. An eigenvalue of A is a scalar lambda such that the determinant of lambda times the identity matrix minus A is equal to 0, where lambda is the eigenvalue and I is an n by n identity matrix because A is an n by n matrix. The equation determinant of lambda times I minus A is equal to 0 is called the characteristic equation of A. Moreover, when we expand to polynomial form, the polynomial lambda to the n plus c sub n minus 1 times lambda to the n minus 1 plus so on c sub 1 times lambda plus c sub o is equal to 0. So we call this one as the characteristic equation of matrix A. This definition tells you that the eigenvalues on an n by n matrix A correspond to the roots of the characteristic polynomial of A. To define how we find the eigenvectors of a matrix, we use this theorem 4.7. Let A be an n by n matrix. The eigenvectors of A corresponding to lambda are the non-zero solutions of lambda times I minus A x is equal to 0, where lambda is the eigenvalue being considered, I is an n by n identity matrix, x is a vector of x variables, and 0 is a zero vector. To illustrate the process, let's consider example 4.10. Find the eigenvalue of the matrix A, which elements are 2, negative 12, 1, and negative 5. The first step in finding the eigenvalues is to identify the characteristic equation of A. We start by stating the theorem. Determinant of lambda I minus A is equal to 0. Then we perform the operation inside the determinant, giving us the matrix lambda times 1, 0, 0, 1 minus matrix A, that is 2, negative 12, 1, negative 5. So this is equal to lambda minus 2, and this one will become positive 12 because negative times negative is positive. Then lambda 0, so this will become negative 1, whereas this one is lambda plus 5. Next, we get the determinant of this matrix, that is lambda minus 2 times lambda plus 5 minus negative 1 times 12. Then we equate this to 0. Then we simplify this, that is lambda squared. So we use FOIL to perform this operation. Plus 5 lambda minus 2 lambda minus 10. And this one will become plus 12. Combine like terms, we have lambda squared plus 3 lambda plus 2 is equal to 0. Next, we factor this one, that is lambda plus 1 times lambda plus 2 is equal to 0. By zero product property, we say that lambda is equal to negative 1 and lambda is equal to negative 2, which gives us the eigenvalues of this matrix, and those are negative 1 and negative 2. Now, let's find the eigenvector for this matrix. To find the eigenvector of this matrix, we will consider the two eigenvalues we currently have independently. So we will consider first negative 1, then next we will consider negative 2. So let's first consider lambda is equal to negative 1. To find the eigenvector associated with this lambda, we have this equation. That is lambda times I minus A times the vector x, which is equal to the 0 vector. Since our lambda is equal to -1, so we will replace that value, that is -1 times the identity matrix minus matrix A, then the vector x and 0 vector. Next, we perform the operation inside the parentheses, that is -1 times the identity matrix minus matrix A, that is 2, -12, 1, and -5. And this one is equal to -1 minus 2. And this one is -1 times 0 is 0 minus -12, so that is +12. So -1 times 0 is 0 minus 1, that is -1. -1 times 1 is -1 minus -5, and that is +4. Next, we multiply this to our vector x. So vector x is equivalent to x sub 1 and x sub 2. And the 0 vector, and that is 0, 0. Before we multiply this operation, let's simplify this. So this is -3. This one is 12. This one is -1. And this one is 4. So x sub 1, x sub 2. And this one is a 0 vector. Let's multiply this, and we will have -3 x sub 1 plus 12x2, and this is -x1 plus 4x2, and all of which are equal to 0. So as soon as we have this, the next step is to find the solution to this system of linear equation. In this case, we will use the Gauss-Jordan elimination. So we have our augmented matrix. We have -3, -1, 12, 4, and this one is 0, 0. So the first step here, in my case, I will multiply the first row by -1/3. So -1/3 R1. So this will become, negative. So this will become 1, and this is -4, and this is 0, whereas this one is -1, and this one is +4, and this is also 0. Next, we will perform this operation, that is R2 plus R1. So basically, what we are looking for is the reduced echelon form of this matrix. So this one is 1, this is -4, and this is 0. Whereas in the second row, that is -1 plus 1 is 0. 4 plus -4 is also 0. And 0 plus 0 is equal to 0. Therefore, the solution of the system is x sub 1 minus 4x sub 2 is equal to 0, where x sub 2 is a free variable. In that case, since x sub 2 is a free variable, we can say that x sub 2 is equal to t. And from that, we may further say that x sub 1 is equal to 4 times t by substitution, giving us the value of x sub 1, which is x sub 1 is equal to 4t. Finally, we write the solution as a vector, that is x, so the vector x is equal to x sub 1, x sub 2, And this is equal to, for x sub 1, we have 4t based on this. And for x sub 2, we have t based on this. And factoring out the common term, which is t, and we have 4 and 1, giving us the eigenvector, which is this. This is our eigenvector, where t is not equal to 0. In other words, the eigenvector of the matrix associated with the -1 eigenvalue, this one, is the non-zero scalar multiple of the vector 4 and 1. So we may write it here. For lambda is equal to -1, the eigenvector is the non-zero scalar multiple of 4, 1. We may write t here to indicate the multiplier or the scalar multiplier of this eigenvector. For the other eigenvalue, which is equal to -2, the associated eigenvector is t times 3, 1. So the eigenvector here is the non-zero scalar multiple of 3 and 1. You may find the solution to this answer by performing this similar process for lambda is equal to -2. For our next example, let's find the eigenvalues and its associated eigenvectors of this matrix, which elements are 1, 2, -2, 1, 2, 1, -1, -1, and 0. So to find the eigenvalues of this matrix, we start by stating the theorem. That is the determinant of lambda times I minus a is equal to 0. Then we perform the operation. Actually, we can make this one short. That is, for the first element, that's lambda times 1. So that's lambda minus 1. This one will become -2. This one will become +2. This one will become -1. This one will become lambda minus 2. Here, this is -1. This one is +1. This is also +1. And this one is a lambda. Next, we calculate the determinant of this matrix. So using the shortcut method, we will just copy the first two columns. And we start multiplying values in here. So we multiply this, this, and this. So this is lambda minus 1 times lambda minus 2 times lambda. This one is equal to 2. And this one is equal to -2. Then we multiply this, this, and this. And this one gives us 2 times lambda minus 2. This one is -1 times lambda minus 1. So I did not include the +1. Whereas this one is equal to 2 lambda. Next, we perform the operation. That is lambda minus 1 times lambda minus 2 times lambda plus 2 plus -2 or minus 2. Then minus 2 times lambda minus 2. And this one is minus -1 times lambda minus 1 minus 2 lambda. We can equate this one to 0 also. Then perform the operation. So we use the FOIL. This is lambda squared minus 2 lambda minus lambda plus 2. Then we have another lambda. So this will become 3. This is squared, and we have a lambda here. Then plus, minus, so basically this is cancelled. So this is 0, 0. And let's continue. We have negative 2 lambda plus 4. Whereas this one is, so this will become positive. So that is positive lambda minus 1. And we have negative 2 lambda here. So we simplify. So this will be zeroed out. And we have here lambda 3. This is negative 3 lambda squared. 4 plus negative 1. Oh, we can add that one later. About this one, this is negative lambda. And this one is plus 3. So this is equal to 0. Next, we will factor this expression in the left-hand side of our equation. And this is equal to lambda minus 1 times lambda plus 1 times lambda minus 3. So by zero product property, we have our eigenvalues, and those are lambda is equal to positive 1, lambda is equal to negative 1, and lambda is equal to positive 3. Next, let's find the corresponding eigenvector for lambda is equal to 1, the first one. So let's consider the first one. Lambda is equal to 1. To find the associated eigenvector of this eigenvalue, so we have lambda times I minus a times the vector x, which is equal to the 0 vector. So to make things short, basically I will just consider the expression inside the parentheses, and that is 1 times I, or simply I minus a, because our lambda is equal to 1. And if we expand this expression, this is equivalent to 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is our n by n or 3 by 3 identity matrix, because our matrix is a 3 by 3 matrix. And for our A, it is equal to 1, 2, negative 2, 1, 2, 1, negative 1, negative 1, and 0. So, if we perform this operation, this is equivalent to 1 minus 1 is 0. 0 minus 2 is negative 2. 0 minus negative 2 is positive 2. 0 minus 1 is negative 1. 1 minus 2 is negative 1. 0 minus 1 is negative 1. 0 minus negative 1 is 1. 0 minus negative 1 is 1. And 1 minus 0 is 1. So we now have this new matrix, this one. So the next step is to reduce this matrix into the reduced echelon form. So the first operation that I will use, I will be switching the third row and the first row. That is R1, R3. So our new matrix will be 1, 1, 1, negative 1, negative 1, negative 1, and this is 0, negative 2, and 2. Next, I will perform this operation, that is R2 plus R1. So our new matrix will be 1, 1, 1. And this one is negative 1 plus 1 is 0. Negative 1 plus 1 is also 0. And negative 1 plus 1 is 0. Then we have this as our third row. Then I will switch row 2 and row 3. So row 2, switch to row 3. So the new matrix is 1, 1, 1. This is 0, negative 2, 2. And this is 0, 0, 0. And finally, I will multiply the second row by negative 1 half. So our new matrix will be 1, 1, 1. This is 0, 1, and negative 1. And this one is 0, 0, 0. So it seems that our matrix is not yet in its reduced echelon form. We need to make this 0. So to do that, I'll perform the operation R1 minus R2. And our new matrix will be equal to, so 1 minus 0 is 1. 1 minus 1 is 0. And 1 minus negative 1 is 2. For the second row, we have the same elements. And also for the third row. Now we have the reduced echelon form of our matrix. So technically, this is equal to 1, 0, 2, 0, 1, negative 1, 0, 0, 0. We multiply this one with the x vector. So this is x sub 1, x sub 2, and x sub 3. And this is equal to the 0 vector, 0, 0, 0. So we now have the solution of our system of linear equation. So that is x sub 1 plus 2x sub 3. Here we have x sub 2 minus x sub 3. And x sub 3 here is our free variable. Therefore, we may say that x sub 3 is equal to t. And subsequently, we can say that x sub 2 minus, instead of writing x sub 3, we have t. And from there, we can say that x sub 2 is also equal to t. And for the first equation, that is x sub 1 plus 2. So x sub 3 is equal to t. This is equal to 0. And from there, we can say that x sub 1 is equal to negative 2t. And therefore, we have our solution. And that is x is equal to x sub 1, x sub 2, x sub 3, which is equal to negative 2t. So that one. For x sub 2, we have t. And for x sub 3, we have t. Or, in other words, we have t. And here we have negative 2, 1, and 1. And therefore, the eigenvector corresponding to positive 1 eigenvalue are the non-zero scalar multiples of negative 2, 1, and 1. So you may use the same method to solve for the eigenvectors associated with lambda is equal to negative 1 and lambda is equal to positive 3. So that's how you find the eigenvalues and the eigenvectors of a matrix. I hope you learned something. Thank you very much for watching and have a great day.